Now that we're well into our discussion about Boolean expressions and their use in conditional statements, our next goal is to take kind of a brief aside and talk about how we can convert between Boolean expressions, or in other words, finding equivalent Boolean expressions. And so we're going to create a few tools that we can use to either convert between these Boolean expressions or to just create expressions in general that have some type of meaning to us. So we're going to start off by looking at the first of those tools, which is what's called a truth table. And we're going to look at a truth table for one of the expressions that we already know, which is just an or statement. So here's what it looks like. So my truth tables, what they're typically going to look like is, a table where I have some input values. In this case, A and B are two Boolean variables. And then their output value in this case, which is going to be A or B. So based on the values of A or B, what is this output? So what I need to do is look at all the potential different combinations of A and B. Since they are Boolean values, that means that they're either going to be on or off, or they're going to be ones or zeros, or true or false. So I'm actually going to start with true and true, and then I'll go with true and false and true and false and false. And so this is all my different combinations of true and false that I can have for A and B. Everything's covered here. Obviously, for every additional variable that I add into this, it will double the amount that I have, but for just two variables, I will have 4 total possible solutions. So, as we are already aware, A or B is true whenever either A is true or B is true, or both of them are true at the same time. And so that means that my output, in this case, A or B, will be true when they are both true. It will also be true when just A is true. It will be true when just B is true. And it will be false when they are both false. So that's truth table number 1. Let's look at another quick example for a truth table for A and B. So if I have A and B as my inputs, and then my output being A and B, then we're going to have the same inputs again. So true and true, true and false, false and true, and false and false. Now we know that A and B is only true whenever both A and B are true. If either one of them is false, then this whole statement is false. So A and B, if they're both true, this will be true. But whenever one of them is false, so in this case B is false, it will be false. Whenever A is false, A and B will be false. And then whenever they're both false, the statement of A and B will be false as well. So those are just two basic truth tables for a couple of expressions. Let us now look at one other kind of tool available to us. Is that it's going to be a pain if we have to keep writing these out using these ors and these ands. So another thing that's worth noting is that there is some kind of simplifying things that's going to make this look more mathematical, because really what we're doing is called Boolean algebra. When I say Boolean algebra, what I mean by that is like this computational practice of working with these Boolean variables. So you will normally see, A's and B's used, or, whatever the variables are. But instead of or, so instead of seeing what or looks like in a Java context, you might also see the word or, which you might see a lot of times, is plus. So instead of seeing A or B, or seeing A or B, you might see A plus B. And there's a very good reason for that we're going to see here in a bit. The other one is, so instead of my 2 ampersands, which I struggle with writing, I could also see the word and, or I can see multiplication, or an implied multiplication. So what I mean by that is A and B could also be written as A and B, or it could be written as A times B, or it could also just be written as A, B, with that implied multiplication there. All those mean and. And then we know that our negation in Java is not A, which you could also see in what I will commonly write is not A. And I'll use this little tick mark here to show the opposite, the negation of that value. So these are all different notations that you're going to see from me at different points in time. So there's that. So let us try then. Let's go ahead and get rid of these. And let us try another example. So let's go ahead and work out a new Boolean expression. The expression is going to be this. So we're going to work with, oh, stop it. We're going to work with the expression AB plus A not B. All right, so quickly we'll just go ahead and talk about what this is saying. So this is saying A and B, or not A and B. So what you're going to see here is that this actually works out in such a way that, or I guess it doesn't work out in such a way, but our order of operations for anding and oring things together is the same as our order of operations for multiplying and adding things. The first thing that I'm going to take care of are these two values, and then I will add them together, or in this case, really OR them together. So what I'm going to do is to evaluate this. So what I'm really trying to do is trying to evaluate when I have different truth values for A or B, what is the output of this? And then I'm going to ask myself next, what is the simplification I can do of this? So I'm going to go ahead and make a truth table with a few different components to it. So I'm going to have A here, of course. I'm going to have B here. Then I think it's going to be useful for me to look at A and B together. And I think it's going to be useful for me to look at not A and B. And I'm going to somehow put those together into this final statement of A and B, or not A and B. So just like before, I'm going to have my same setup. I have true and true. Actually, the other shorthand I'm going to do is I'm going to start writing these in terms of ones and zeros. So 1 being true and 0 being false. So 1 and 0 and 0 and 1 and 0 and 0. All right, now here's the fun part of the video where you're just going to hear me saying a lot of trues and falses and zeros and ones, just kind of in rapid succession. So whenever I have A and B, so when they're both true, then A and B will be true as well. When either one of them is false, then this will be false, and this will be false, and this will be false. Now, a little bit trickier is not A and B. So this is only true, and if it's easiest, I think just to find the one situation where it is true, which is whenever A is false and B is true, which is right here. So this is a 1. Otherwise, this will not be true because in the first one, so not true for A is false, anded with true is still false. The second one, not true, so false, anded with false is false. And then not false, which is true, anded with false is still false. So these are my portions, not A and B, and then also not A and B. And now what I'm going to do is I'm going to OR these things together. I could have done this all at once, but I think it's just easier to kind of do them individually and then combine them. And so I need either one of these to be true. So in this case, true or false is true. False or false is false. False or true is true. And false or false is false. Perfect. Okay. So the question is, by looking at this truth table, we can be a little bit clever here. And what we're going to notice is that is there a way of simplifying this? And the answer is yes. If I actually go back and look, what we'll notice is that my truth values for this expression are actually the exact same as just whatever B is. And so it kind of seems that A doesn't matter at all, and that it's just B that really matters in the outcome of what this expression here is. And that is actually exactly accurate. We just have to justify as to why. So the other reason that Boolean algebra kind of works out nicely is that this expression simplifies the exact same way that our algebraic expressions do. And so I can even do some factoring. And that we won't justify it, but it does work out in the ways that we would want to. So in this case, I can factor out a B from both of these and rewrite this expression as B And then if this was an algebraic expression, I could factor out the b, and what I'd be left with then is an a and then not a. And so in other words, it's saying that, for both of these to be true, like I just need b to be true. So it's either b is true and then either a or not a. So this expression actually makes exact, same sense. So the question is, what is a or not a? Well, both of these can't be false. One of them will always be true, because if a is true, then this left-hand one will be true, and this will be false, or together will give me a true. And then if a is false, then this will be false, and then not false, which is true, so this will also be true. So this simplifies to be, this is b and, always true here, and so this is just simplifies to b, right? So I can use my algebraic expressions and my algebraic kind of knowledge and how I simplify these things to work out what these Boolean expressions are equivalent to. So that's one example. Let us look at another one then. Let's look at, here, let me get rid of these. Go away, add a new one. Perfect. Okay, let's look at a new expression. Then we're actually going to look at two here. Switch my color back. So I want to look at the expression a or b, but then not that. And then I also want to look at the expression in a second here that is not a and not b. So we're going to look at these two things. So I'm going to make my truth tables just like I did before. This may be too big, but that's okay. A or b and not that. And then I'm going to do the same thing over here. Make my truth table, a and b. And then this is going to be not a and not b. All right, so 1 1 1 0 0 1 0 0 1 1 1 0 0 1 0 0. Okay, so stepping through the first one. Whenever a and b are both true, that makes the inside part of this true, but not that, so that's false. Whenever I have the inside, so a is true and b is false, that means it makes the inside true, so this is true, and not that is false. The same thing goes, they're just flip-flops, so this is also false, and so then whenever a or b, they're both false, it makes the inside false, and the opposite, which would be true. Okay, and then I'm going to do the same thing over here. So not a and not b. So whenever a and b are both true, that means that, so that is false, anded with false, which is just 0, so false. Whenever a is true, so that makes that false, and then b is false, which makes this true, but anded together, I get another 0. The opposite's going to be true when they're reversed. And so whenever a is false, so not that is true, and then b is false, so not that is also true, true and true gives me true. All right, so what I can see here, and this is the interesting thing, is that these two expressions are equivalent, which is interesting. And so this is actually so interesting that it has its own name. This is called De Morgan's Law. De Morgan's Law. And it tells me this: whenever I have an expression which is a or b and not that, what it is equivalent to, and I really hate this next part because, like, as a mathematician, it just kind of sounds gross to me. But if we were to distribute the not, if we were to distribute here, different color, distribute the not to both of these, and then switch the operation that we're doing, we get our new expression. So this is equivalent to not a, not b. And so the reverse is true if I have this other expression as well, which is that if I have a and b but not that is equivalent to not a or not b. So this is De Morgan's Law that says that these two very different statements, or seemingly different statements, are exactly equivalent. And so in our simplifying process, whenever, I just realized that portion that's cut off. Oh well. How about I draw some arrows the other way? Whenever I go through my simplifying process, this is one of the tools that I can use to simplify or to change my Boolean expressions. So let's look at then a few examples. Let's look at a few examples. Let me make something up. What's a good one? Ooh, that, no, yep. How about we just go with this one? All right. We're going to take a look at maybe 3 different examples, which I would highly suggest you, what you do is, watch these as I write them down and then try to simplify them on your own. So the first one is going to be A and B, or not A and B, or not B and A, or not B and not A. All right, that's number 1. Number 2 is going to be A and B, and then not C, or not A, B, and not C. And the third one is going to be, all right, that's a little tricky. Not A and not C, knotted all together, or not B, or A and D, but not that. Okay, so here are 3 expressions. I'd highly encourage you to stop it here and try these out, but I'm going to roll right in. So the first one, what I'm going to do is it's kind of like factoring by grouping is what I'm going to do. So I'm going to look at the first 2 terms and then the second 2 terms in kind of pairs. So I'm going to factor out a B in the first one, and what I'll be left with is A or not A. And in the second one, I will factor out what they have in common, which is not B, and what I'm left with A or not A. So when I simplify this, as we kind of talked about previously, A or not A is just true. Well, one of them has to be true, and since it's ORing together, this will just be B or, and then not B. And as we said just 5 seconds ago, is that if I have B or not B, then this has to just be true. So this actual whole statement evaluates to true, which kind of makes sense, because what I'm doing is I'm ORing together 4 statements here that basically kind of encompass all my different possibilities for A and B as far as their either original state or the negation. So one of them is always going to have to be true, and so this evaluates just to true. That's it. Okay, next one. So same thing here. I'm going to see what I can factor out, and looks like the only thing, actually there's 2 things I can factor out. I have B and not C here, and B and not C here, so when I factor this out, I will have B and not C, and what I'm left with is A and not A, which is just true, and so this whole statement just simplifies down to B and not C. Simple as that. Okay, so this last one then is a little bit tricky because I have to use De Morgan's law here to help me simplify. So what I'm going to do is I'm going to distribute. Darn, I'm off again. I'm going to distribute my not, and so what I will actually have is A or C, and then I will have not B, and then when I distribute here, I will have not A or not D. Okay, and so here's the thing, is that I'm ORing 5 things together. If any one of them is true, this whole thing is true. So like this thing already has pretty good odds being true no matter what. But actually what I have here is I have an A and I have a not A. One of those will always be true. So this whole statement actually simplifies to just true as well. And that's it. Okay. So that is how we can be given expressions and simplify them. And if we wanted to, we could obviously make truth tables here and compare and actually make sure that they work out the way that I want them to. So now the question is, can I work my way backwards? What if I'm given a truth value, and I want to figure out what the Boolean expression is. So for example, if I have going to have 3 inputs this time. So I'm going to have A, I'm going to have B, I'm going to have C, and I have some mystery output which I would like to write an expression for. And so here's what my table looks like. So I'm starting off with the false values, 0, 0, 1, 0, 1, 0, and 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. All right, and my output then is 0, 0, 1, 0, 1, 0, 1, 0. Okay, so the question is, how can I go from this truth table and then make a figure out like what the expression that would be that satisfies this? And so I could just try to logic through this and like look at the zeros and ones and be like, okay, what's the pattern? Like, seems like A is pretty much always true, which actually that's not true at all half the time though. And so it's like, how could I do this? And so there's kind of a brute force way of me doing this, and the way I'm going to do it is I'm going to look at all my true values. So I've got 1, 2, 3 of them here, and so I'm going to look to see what makes this true. And so what makes this true is that whenever A is false and B is true and C is false, that is one way that I can make an output it true. Another way, or I could have A be true, B be false, and C be false. Or I could have A be true, B be true, and then C be false. So those are my 3 options. The only way to get a true output is by this. So the question is, how can I simplify this? So I'm going to look again to see if there's anything I can factor out. It looks like there is a not C in all of them, but that doesn't work. And okay, so let's do this. So let's factor that out. So I'm going to factor that out, and what I'll be left with is, all right, so A not B, actually it's not A and then B, and then this is A not B, and then I have A, B. Okay. So the question is, what can I do with this? And the answer is now I have to be just a little bit clever here, because what we're noticing is that well, there's a couple. We could brute force this by making an algebraic manipulation here, or we could kind of think about this. So how am I going to get A and B to be true? Well, this is, or I guess this middle part. How am I going to get this whole middle part to be true? And so the thing is, you'll notice that if both A and B are true, then this whole thing is true. If just A is true and B is false, then that part is true. If just B is true and A is false, that's true. This is kind of remind you of something, and what that thing is this is actually equivalent to A or B, right? If either A or B or both are true, then this whole thing is true. So in this case, I hope I didn't just lose my marker. Okay, cool. So in this case, I can, just by logicking through this, acknowledge the fact that this is going to be equivalent to not C and then A or B. So the question is, how could I get there, though, and justify this? And my answer is obviously going to be, well, it's actually a little bit tricky. Actually, there's no great way of doing this. So I can algebraically manipulate this and change it to, okay, let's say I want to factor out an A from the last 2 terms. So if I do that, I'll have not A and B, or A and not B or B. Okay, perfect. And we know that this right here will always be true. So then what that means is that this will simplify down to not A and B, or A. And so we could get here and we might stop and we might think that's actually all we can do, but here there's a little cleverness that comes in here as well. So if A is true, then this whole thing is true. But if A is not true, B is going to actually save us. If A is true, then B can save us, and this whole thing will be true. So there's actually this inner part, and this is just a true statement in general. A or B is equivalent to A, not B, and B, or it's also equivalent to, how do I flip this? A or B, not A. So these are all equivalent statements here. And so this whole thing will simplify down to not C and then A or B. And if we wanted to, we could expand this out. I don't know if it looks nicer either direction, but I think this is slightly better. Okay, so that's how I simplify this statement. I took it from my truth table up here, where I just found all the different values that made my output true. I ORed them all together, and then I simplify. Okay, so that's skill number 2, I think, that we have so far. And so the last thing that we need to talk about then is, and this is the thing that's probably going to be the most useful to you, is the fact that, believe it or not, you're not going to probably working with just a ton of like Boolean values just ANDed and ORed together all over the place. What you're going to be doing is working with a lot of mathematical expressions, most likely. So for example, what if we talked about, what if I had the expression which is x is greater than 5? Okay, so that's a Java syntax right there. What if I have not that? What is this equivalent to? So what this is equivalent to is the opposite value of what x is greater than 5 is. And so what are all the values that are not greater than 5? Well, that would be the values that are less than 5 and the values that are equal to 5. So this whole equivalent, or the equivalent statement here, is x is less than or equal to 5. Okay, so we can take algebraic inequalities and apply our negations to them. And so now we can look at a really good justification for De Morgan's law then. So what if I gave you the statement that is x is less than negative 5 or x is greater than 10? So if I go and I graph this really quick on my number line, I will have negative 5 over here someplace, and I will have 10 over here. And so if I want to talk about x is less than negative 5 or x is greater than 10, that means that I'm going to have all the values starting at negative 5 and going less than that, and all the values starting at 10, but not including 10, or negative 5 for that matter, and then going to the right. So what if I instead had not x is less than negative 5 or x is greater than 10? So De Morgan's law tells us that we can negate both of the things in here and then switch this to an and then I'm good. So in this case, what that would be is x is greater than or equal to negative 5 and x is less than or equal to 10. And if I go look at my number line over here then, so x is greater than or equal to negative 5, so including 5 and then going in this direction, and then x is less than or equal to negative 10, so going in this direction. So it's all these values. This is the negation of my original statement. These are negations of each other. Okay, which is just, we got from one to the other using De Morgan's law, but then justified it using our number line. So that is skill number, I guess we're on number 3 maybe at this point, or 4. I don't know, there's a whole bunch of skills. But point being is that at different points in time, whenever we're writing our program code, we will have to take our Boolean statements and maybe simplify them in such a way that's easier for us to understand, because obviously they're all equivalent to the computer. But this is just a way for us to make better sense of things and to be able to convert between different expressions depending on what the situation needs. So having this skill kind of in our back pocket as we go is going to help us out as we continue our journey through talking about Boolean values and conditional statements.